Okay, well, you had a little mini break because I was away at a conference. Hope you enjoyed your Thursday. And I've already helped a number of people. This homework assignment that's due today about, how to wire in these chips into an address space is apparently, conceptually, it's a little bit tricky. I mean, anyway. So I've already helped a number of people, and so let's go ahead and continue the discussion for those of you who have questions about how to do this.
1B, can we go over partial mapping?
Partial address decoding?
Yeah.
So this is exercise 21B. So this is the partial address decoding one. All right, so that is on this slide is the example that you model it after. And what we have is in figure 11.46, we have a memory map with, of how we want it to be populated. And then I assume then that you know how to do the full address decoding, right? And so this table in figure 11.47 shows the minimum address and maximum address of each device, and then those address fields that change depending on between the minimum address and maximum address are denoted by X's. Okay, and so we saw then how that is reflected in figure 11.48. The key idea is you use the chip select to decode the signals from the high order address lines, right? And select the chip whenever it needs to be selected so that it's mapped where you want it to be mapped in the memory map. Yeah? And then the idea is with partial address decoding, you want to minimize the circuitry that you need to wire the chip into the right spot in the address space. And so what we do is we line these up vertically. We line up each memory device vertically, and we inspect the high order bits, the high order bits of the address line of where that's going to be wired in, and then we see which high order column of the address is unique to that one device. And we might have to choose a group of 1 or 2 or 3, a small number of address lines that will uniquely identify that chip. And so if we can uniquely identify that chip based on a fewer number of address lines, then we don't have to worry about using the other high order address lines to decode that chip to place it in the right spot. So in this particular problem, exercise 21B, you were able to get it, you were able to write this down, right? Because this is the key. This figure right here on this slide is the key to analyzing partial address decoding. And how did were you able to identify a column that would make one of the devices uniquely identifiable?
All three kind of uniquely.
Well, I think as I recall in exercise 21B, I was helping another student earlier today, and I think there were 2 chips that had a unique, there's only 3 chips in the exercise. I think either the first one and the last one, you could start with either one being uniquely identified by just one address line.
Yeah.
So now, do you have a question? What's your question?
More of just the next step of the...
The next step. Okay, so here, let's do this. For exercise 21B, let's write down, does everybody know the address space the address lines that we should write down? So somebody read them off for me.
00
00
00 XX
0, 0, x, x,
X, X, X, X.
x, 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 x. So does everyone agree here on this one? Okay, and what was the next one?
0, 1,
0, 1,
1, 0, 0.
1, 0, 0,
And then the rest are X.
x, 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 x. And then the last one is what?
1, 1,
1, 1,
1,
1,
1,
1,
0, 0,
0, 0,
0,
0,
0.
0, x, x. This must be a 4-port I/O, right? Because this will access 4. So now here, there's 2 ways to do this one. I can see right off the bat. You could either, there's more than one way to skin a cat. So, my father-in-law used to always say. So if we look at this one, we see that this one bit in A0. Wait, how did we number these?
A9.
Yeah, this is A9. Is this A9, A7, A6, A5, A4, A3, A2, A1?
You missed 8.
Oops. A9, A8, wait.
You missed 8. You went from A9 to A7.
Yeah, actually, let's put this up. So this one is A9, this one is A9, and this one is A0, right? So 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Good. Okay, so there's a couple of ways to do this. One is we could see that this uniquely identifies this chip, and then we could do our analysis on the other ones. Or, so we could start this way, or we could start, what's another way to do it?
A8 on the first chip.
We could start, we could say, oh, a 0 on this line uniquely identifies this as compared to these. So either way is fine, I think.
Can we do that one?
Well, has anyone done this one way or the other? And besides, yeah, I know you did it that way. Oh, you did it this way?
Yeah.
This is a 0, right? Okay. So now, yeah, there's a couple of ways to do this. So now, I guess, then what did you do? Did you do these two?
Yeah.
Like this?
Exactly.
So if the first 2 bits, first 2 values on the address line are 0, 1, then we select this chip, and if the first 2 ones are 1, 1, then we select this chip. All right, so, but now here's the problem. Here's what you have to do. When you draw your memory map with the clones, the question is how many, let's just count how many clones there are.
Do you need to do 1, 1? Can you just do 1? Can you just use the first one?
On this one?
Yeah.
Oh, that's a good question. Let's analyze that. So the question is, could you do it like this? Because after all, this one being unique is like this. Now, can somebody tell us whether or not that's a good idea? We could do that, even make it smaller than before. Can anyone? That's a good question. That's a really good question. Because look, this will uniquely identify this, this uniquely identifies this, this uniquely identifies this.
But the first one, you can make it 1, 0. And you can make the bottom one 1, 0 as well.
Yeah, the problem is and that's exactly why you cannot do it this way. Because if we had A9, A0, if on our address, sorry, A9, A8, A7, etc. If actually what was on the address line was a 1, 0, now watch, think about this. Think about this. You're asking if we could do this. The problem is if we have a 1, 0, we would be selecting both this one and this one. And we would be having both chips selected at the same time.
Okay.
Are you with me on that?
Well, yeah, but if you're,
Because then they would both be putting their data on the bus at the same time and you'd have conflict.
right, but if you're saying the first one could be a 1, then,
Your question was, can we select this one? Can we select this one by saying, if there's a 0 on A8, we'll select this chip. If there's a 1 on A9, we'll select this chip. The problem is, if the CPU puts out a request for address 10, it will be selecting this chip and this chip. And that data will be it will have two outputs of the chip on the bus at the same time. So their tri-state devices would be enabling them at the same time, and we'd have conflict.
okay.
Now, are you with me on this?
Well, I just don't get why the A9 could change, but not the A8.
Think of this as, don't think of this as being changing. Think of this as the CPU is requesting the memory subsystem to put information on the bus. Are you with me? And what we want is we want to have a memory map where this one is mapped at address 0, this is mapped at address whatever this 0000 is, and this is mapped at this address 110000, what this address. And we don't want there ever to be a conflict of having them both on the bus at the same time.
Right, I get that, but it's not an X, it's a 0, so. Like,
But, well, okay, so here's my question. If the CPU were to put this address on the bus, 10000000, what would happen if you design it this way? What would happen? Well, because there's a 0 in this, it would put the data lines of this onto the bus, and because there's a 1 here, and you're doing it this way, it would also put the data lines of this device on the bus, and that's a conflict. Are you with me? See, look, you could do it. Here's what you could do. You could either do it, check this out. Watch this. You could either do it this way, or you could do it like this. Or you could do it like this. Now wait, how did we have it? We had one here. Or you could do it like this. Here, and then this one would be here. Now in this particular setup, what would happen? Which chip would be selected? Well, this 1 would select this, right? And the fact that this is 10 means this would not be selected, nor would this one be selected. Maybe that clarifies it.
Okay, so you're just saying that it has to be like unique.
Yes, and you can't have there be a conflict where both chips are put on the bus at the same time. Yes, Shane.
So then that setup would be acceptable if you had the 00 on top so that you could have the 1 just on the bottom?
Yes.
Okay.
What we just did was two different approaches, both of which would work.
Good, I did the second one.
Yeah, that's why I said, did anyone do, yeah. Yeah. This one is actually kind of nice because then the clones are a little more easy to figure out. Now, but you had your original question was, did this answer your question actually, or?
The next part would be my question.
Okay, yeah, so let's talk about the clones. All right, so now look. The question is, where are the clones? Right? If we're only going to use these bits to select this device, that means, and we're going to ignore these bits, that means that where are the clones? Where are the clones of this first device? Here, let's do this. Clones. Where are the clones? The clones are at what? Well, first of all, let's do the original. Where is the original device? At what address is the original device at? The original device is at address 0000, 0000, and then 000000, 000000. That's the original. That's the starting address of the original device, right? And then there's going to be a clone. And now, where else is there going to be a clone? There's going to be a clone at 0001. Are you with me? So clones. 0001, 000000. That's going to be one clone. And there's going to be another clone at what? 0010, 000000. And there's going to be a clone where else? At 0011, 000000. There's going to be, because, and why is that? That's because these, it's going to select the chip. That's how you analyze that.
Can you draw the slash?
Going through this, show where the,
So for the last one, in this case, we'd have 1, 2, 3, 4, 5, 6.
how many clones do you have here? How many clones do you have here? You have 4, wait.
3.
You have how many there are here, wait.
You have 2.
No, wait, is there another clone?
No, you have 2 squared options, but one of them is the original. So you have 3 clones.
Right.
So on the last one,
Right. So the total number is 2 to the 2. So we have 4 devices here, one of which is the original. How many devices do we have?
we have 2 thirds, we have 8. So
We have 2 to the third, so we have 8. So we have 7 clones. And how many clones do we have here? 1, 2, 4, 8, 16, 32, 64.
Wait, isn't there 7 right? 2 to the 7th is 128.
2, 4, 8, 16, 32, 64, 128. Oh, is that what you said? Yeah, 128. 127 clones.
So on the map, would you want us to draw?
I obviously don't want you to do 127 arrows.
Because on the last one, so it would have,
But you got to make sure that those clones don't
they don't overlap.
Overlap.
They're only 4 bits, right?
what?
They're only 4 bits.
Yes, each one is only
So then, how do we draw that without drawing every single line?
well,
Can we just draw a block?
or block, and just put how many, yeah. Of course, I don't expect you to write 128 boxes on your memory map. This is a really good go ahead.
Can you go over or to how, for the last one, there are 128 clones?
Because okay, do you understand that the original address, or the address of the original one is at 1111000000. That is the address of the original. But now, here's the thing. This device is going to be selected whenever there's a 1 in this and there's anything in the remaining 1, 2, 3, 4, 5, 6, 7 bits of the address.
Yeah. So, oh, okay.
And so there's actually all of the possibilities of this, 2 to the 7, it's going to be selected.
Okay.
And 2 to the 7 is 128.
But then one of those.
But then one of those is the original, so it's 127.
Okay.
The original one is kind of in the middle.
Yeah.
See, that's what happened on this example. Look, do you see here in this example on figure 11.50, what happened was that 8-port I/O chip was at this address in the middle, and then the clones were to the left and to the right.
Yeah.
That it was the same phenomenon. Whereas here on figure 11.50, the original RAM was here, and then there was a clone. See, this is right slash, and then the clone for the RAM, that's right slashed, you know, is here. And then the second RAM was here, and then its clone was next to it here. Whereas with this one, the I/O chip was in the middle. Actually, it was this blue shaded one, and then the cross-hatched ones are where are where the clones were. Now, what was this? Oh, and there was just one ROM at the end that didn't have any clones. Yeah.
Okay, yeah.
Why did the ROM at the end not have any clones?
Oh, good question. In this, the question is, why did the ROM at the end not have any clones in figure 1150? That is because, look, do you see this 32 by 8-bit ROM? Notice that every single bit was used. So there's no difference between this and the full address decoding. Oh, good question. This is really a good exercise to understand the whole concept of a memory map. And how these different devices get wired into the system. A question about number 20. Which one was that? So that's exercise 11.20. Okay, so now, first of all, it said, the problem specifies that there are how many?
It's a 16-bit wide data bus.
It's a 16-bit wide data bus. I think it helps, even though it's going to take a lot of room, to actually draw those lines. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And this address line is A0, and this is A1, dot, 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 down to A15. Are you with me? So now, there's 3 kinds of lines on a bus. There are address lines, and there are data lines, and there are control lines. The data lines are bidirectional.
Right.
Are you with me?
Yes.
Okay? So this is a picture of the address lines. Now, the data lines are another. Wait,
Wait, those
I
are
said
data
this, I said address. These aren't address lines, these are data lines.
those are
aren't-
data lines.
Yeah, sorry, yeah. This should be D0, D1, down to D15, because it said it was a 16-bit
It says a 16-bit wide data
bit
bus.
wide data bus. So look, so here, so this is the data bus. Are you with me? Now, what kind of device did it say for part A? Let's do.
A 1K by 1 dynamic RAM chip.
All right, now let me ask you a question. If I ask you to draw a block diagram of a 1K by 1 chip, what would it look like? So tell me what to draw here.
10 address lines.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10 address lines.
And 1 data line.
Okay, so this would be A0, A1, dot, 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 down to A9, right? Okay?
And then 1 data line.
And 1 data line, because this is, and this is D0.
So we need 16 of those chips.
And here's the point. Yeah, in order to fully populate the data bus, you've got to have each one, a memory device connected to each one.
Right.
Now, this is, here's something else. When the CPU requests memory from, or requests data from memory at a particular address, and we know that all memory is byte addressable.
Right.
How many bytes is this? It's 2 bytes. So when the CPU requests data from some address in memory, what gets put, the memory subsystem has to put what on the data bus? It puts the byte at that address and then at that address plus 1. In parallel, that is simultaneously. Are you with me? So if the data bus is 16 bits wide, then the address that gets put in is the address of the first byte, and then it's that address plus 1 is the next byte. But in order to fully, but what that means is that for any address, you've got to have a device hooked up to every single one of these 16.
Right.
So therefore, how many chips is it going to take?
16.
It's going to take 16.
Okay, so that's the part that I understand. It's the part where it says, what is the smallest number of bytes of memory this computer can have?
Well, that's it. Figure out how many bytes of memory that is.
So it's 1024 by 16 bits.
Yeah, and how many bytes is that? Well, and how many bytes is that?
It's, well, 2 to the 14th bit, so 2 to the 11th bytes. So you have to convert it from bits to bytes.
Yes.
Wait, I'm confused. Wait, how many bytes is that? It's 1024?
This particular chip is 1024 bits. Are you with me? But how many are you going to hook? How would you hook these devices up to fully populate the data bus? How many of these chips would it take?
16.
It would take 16. And one of the D0 of one would go to the D0 of this. The D0 of the second one would go to the what? To the D1. And the D0 of the third would go to the D2.
Yeah, but so if there's confused where if the chip is 1024 bits, and then the data bus is 2 bytes?
Yeah, it's 16 bits. So it's going to take, so in order to fully populate the data bus, this has to go, one of these goes to one, then the next chip would go to the next one, the next chip would go to the next one, its D0 would go to the next one. And so therefore you're going to need how many chips?
16.
16.
So you keep that number.
So now you got 16 chips. You know how big how many bits are in each one, so you know how many bits total are in your memory, and then divide by 8. Sorry.
Divide by 2 to the third.
Divide-
Yeah, 8.
Well, if you do 1K by 16.
Yeah, divided by 8, because that's how many bits. So you divide by 8 to get how many bytes.
Do you want us to actually write out the number, or can we leave it as 2 to the 11th?
I don't care.
So when you have a chip, say we have like a,
The number would be nicer, but whatever.
I can do that. I can do it in my head without using.
Yeah.
So because this is 1024 by 1,
Yes.
that means there's 1024 bits.
Yes. By 1 means one data out.
Right, so what if it was 1024 by 2?
Well,
Actually,
then it would be
that's
1024, and there would be 2 out, and then how would you hook those up?
So then you'd only need 8 of them.
Yes, and what would happen? How would you do that? The D0 of the first would go to the D0, and the D1 of the first would go to the D1. Then the D0 of the second would go to
D2.
D2, and the D1 of the second would go to the D3.
Yeah. I more have trouble understanding how you know that's the smallest number of bytes of the memory.
Because that's the minimum number of chips that you need
Yeah.
to fully populate this.
So
You
have
could
more
add
stuff.
more. Yeah, sure. You could have more if the address bus is bigger than 10 in this particular example. If it's bigger than 10, then you would go to the memory map,
Right.
to the address decoding, and wire them in at a certain address space.
Okay.
You see what I'm saying? This is an example of the first problem,
Okay.
which is a separate issue from how you populate the full address space, by wiring them in at a certain place in the memory map.
Okay. So
Are you with me on this?
It's more like inside the actual chip itself. So if something's like a 4 by 2, there's 8 bits in it. Do you multiply them?
Yes,
Makes sense.
yes. Yeah, and then the first number, when you have an, I forget the letters that I used. Was it N by K or N by M or
Yeah, you use N by M and L by M.
N? Here, if this is an N by M, This N is not the number of address lines. This N is 2 to however many address lines there are. And then this M is how many data lines in parallel coming out of the chip there are. Okay, are we good? These are all really good questions. Are we, is everything good? Okay, now, so let's continue on then with our discussion of the two-port register bank. Now, remember at the end of class last time, far ago, if you can remember back that far, we introduced this component called a two-port register bank, okay? And it's shown here in figure 11.51. And let's see how this, let's review how this looks. So now, here, let's, clean this up a little bit. So we said, talk about remembering from far ago. Those of you who took computer systems are not taking computer systems now. Remember what the registers are in the CPU? They're actually shown here. We have A stands for what? Accumulator. X is the what? Index register. SP is the what? Stack pointer. PC is the program counter, and IR is the? No, X is the index register. I got you. And so IR is the what? It's not the index register, it's the what? That's the instruction register. X is the index register. Right? Does everybody remember that? Okay. And those are the registers that are visible to the ISA at the ISA level. What is abstraction? Hiding detail. So which details are hidden at the ISA level? T1, T2, T3, T4, T5, T6, and M1, M2, M3, M4, and M5. Right? And this T stands for temporary register. So T1 is a 1-byte register, T2 is a 2-byte register, T3, T4, T5, and T6 are also 2-byte registers. And what did we say the M registers are? What kind of memory was that?
Constant one.
Yeah, constant. So what kind of memory is always constant?
ROM.
ROM, that's read-only. And so these values are actually burned into the device. And so what values do we have? We have 0, 0, 0, 1. 0, 0 is at address 22. 0, 1 is at address 23. 0, 2 is at address 24. 0, 3 is at address 25. 0, 4, 0, 8. And then, so we have a bunch of the little ones, and then we also have a bunch of the kind of big ones, like 0xFA, FC, FE, and FF are the bit patterns at address 28, 29, 30, and 31. Right? So each one of these little kind of like half registers is a byte. Are you with me? And how many of these, and so they're addressed from 0 to 31. So how many lines does it take to access a 1-byte register if there's 32 of them? 5, because why? Because 2 to the 5th is 32. Is everybody with me on that? So we said, and so what does this little slash mean? This little slash means that this A line is really 5 lines, and this B line is really 5 lines, and this C line is really 5 lines. And this load clock is just 1 line. And how big is the A bus and the B bus and the C bus? Each one of those is actually how many lines? 8. Are you with me? Okay? And how does this is a block diagram of the register bank. And how does it work? This is basically just, you know, a memory, just like we did our memory module, right? And these really are very similar to D flip-flops. This really is static RAM, because we want this to be fast. This is in the heart of the CPU. We want this to be fast. And so here's how it works. Whatever 5 lines on the A input, whatever those are, those 5 lines access one of these little memory cells. Are you with me? And it puts that on the A bus. So if A, I think we did an example last time. If A has the value, if A has the value 0, 0, 0, 0, 0, B. Oh, not 0, 0, 0, B, because it has 5 lines. 0, yeah, sorry. Zeros 1, 2, 3. Let's do 1, 1. So if A if the values on those A lines are 0, 0, 0, 1, 1, then what does that do? That takes the what? The right half of the what? Of the index register, and it puts it where? On the A bus. Are you with me? That's what that does. So it puts the right half of the index register onto the A bus. And similarly, if B is 0, 0, 0, 0, 1, 0, 1, what does that do? That puts the what? The right half of the what? Stack pointer on the what? On the B bus. And if C is 0, 0, 1, 1, 1, if C is 0, 0, 1, 1, 1, and load CK and load CK, you know, and we clock, we put the clock pulse on load CK, what does that do? That takes what?
The C bus.
Whatever is on the C bus from down here, wherever that is, okay? Whatever is on the C bus, and it clocks it into where? The right half of the program counter. Now, does everybody see how that works? And this is all the lines that we have that control this register bank. A single load clock, 5 A's, 5 B's, and 5 C's, 8 B bus lines, 8 A bus lines, and 8 C bus lines. And notice that the data lines in the CPU are not bidirectional. Why do you suppose they're not? Because what did we have to sacrifice when we did? Why do we have bidirectional data lines? Why do we mess with bidirectional data lines and tri-state devices? Why do we mess with them?
Less transistors.
To save what?
Money on buying more chips.
Well, isn't it less wires?
Oh, it has to be one direction because it's faster.
That's why these are one direction, is because it's faster. Because bidirectional is what? It's slower. But, no, slower, but fewer wires. Bidirectional lets us use the same wires going one way as the other way. But it takes time to set up the tri-state devices, to synchronize all those tri-state devices to be set up correctly so that there will be no conflicts. Do you remember? Good, that was good. Is everybody with me on this? But inside the CPU, everything's unidirectional because for speed. Yeah? Okay, so that's figure 11.51. Now, check this out. 11.52 now is a figure that shows the implementation of that 32 byte register bank. And look at here, you guys. Do you see up here where it says 0 and this rectangle? What the heck is that? What is this 0 and this rectangle and this fat arrow coming in and this fat arrow going out and this one little arrow coming in on the left? What is that? What does that look like? Do you see what we're pointing to here? What does that look like? That looks like a single what? Register. Let's go back and look at the block diagram of a register. Here, figure 11.36. There's the block diagram of a register. Remember what that looks like? Here is the implementation in part B, the implementation with D flip-flops. And here is the block diagram of the register. And what do we have? We have the data coming in from the top, the data in coming into the top, the data out going out, and then the load line is what's coming in to clock it in. And that load line goes to the clock input of the D flip-flops. Now, does everybody remember this? Are we good? Okay. So now when we go all the way to our implementation here, what do we have? How many registers do we have? 0, 1, 2, 3, ... all the way up to 31, actually. There's 32 registers, but they're addressed from 0 to 31. Are we good? And look, and each one of those has 8 bits coming in. Those are the D inputs, 8 bits going out. Those are the Q outputs of the D flip-flops. Are you with me? And the one line coming in to the left, which is the clock. Yeah? And look, what do we have over here? A 5 by 32 decoder. And the C, are you with me? The C input is going to the 5 by 32 decoder. And furthermore, the C bus coming up here from the left is going to what inputs? Going to the D inputs of each in the registers. So here what we said, if C is 00111, what is the output of that 5 by 32 decoder? They're all those outputs are what? Practically all of them are zeros, except for number what? 7. Number 7, the 8th one. Yeah? And then that's the one that's going to be enabled to and here's the load clock. So the load clock here, when we do the load clock, it's going to be disabled for all of them except the one that has the C address on it, and it's going to go into that register. Now, is that clear? Does everybody see how that works? It's all just plumbing, you guys. It's all just plumbing. And now, how do we have an A bus and a B bus? Well, here is an A bus, and here's the B bus. So the A bus is on the top here, and the B bus is on the bottom here, right? So now, how in the heck does that work? Each one of these A bus and B bus is the output of 8 32 input multiplexers. Now, what does multiplexer mean? Many to one. Are you with me? And so let's take a look at this register 0. The D output of register 0, 8 of them are going into this A bus 32 input multiplexers, right? And so on up to, it's going into the A bus multiplexer, and also is going to the B bus multiplexer. And so how many of those pipes are coming in there to the A bus? 32. And what are the A line address lines going to do? They're going to select what? Those A lines are going to select, yeah, which one of those 32 to send out? All right. But there's 8 of them. Why do there have to be 8 of them?
You have to put 8.
You have to put, you have to put D0 in parallel, D0 and D1 and D2 and D3 and D4, D5, D6, D7, and D8. So can you visualize how those are connected inside? Because that's 8 32 input multiplexers. So what does a 32 input multiplexer look like? A multiplexer is many to one, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. 1. That looks like SpongeBob. Rorschach test. See what's there lurking in our inner psyches. Are you with me here? And so this is the D. So one of these for the D0, another one for the D1, another one for the D2. Okay. So anyway, and similarly for here. So do you realize what that means? It's actually possible to have the same number be on A and B, and that same, it will be duplicated on both the A bus and the B bus. I mean, it's not that you'd ever want to do that very often. I can't think of a time when you'd want to do that, but you could. You could actually have the same register be presented on both the A bus and the B bus at the same time. Is all it takes is for A and B to have the same address. Is everybody clear on how this works? So that's the implementation. And that's what we mean by a port. You see what we mean by a port? You have 2 ports, so you can select any 2 and have them output on those ports at the same time. And so what we're going to see next time is, so remember this, an A bus out and a B bus out and a C bus in. Are you with me? An A bus out and a B bus out and a C bus in. Address for the A, address for the B, address for the C, and then a load clock. All right. Excellent. So we'll see you all tomorrow. Same time, same station.